Welcome to the Minnesota Stormwater seminar series. I am John Gulliver. I'll introduce the seminar series and introduce our speaker. So the seminar series has been, is kind of joint between the Water Resources Center and the St. Anthony Falls Laboratory, both from the University of Minnesota. John Bellotta, representing the Water Resources Center at the University of Minnesota, is here. John, please raise your hand. All right. It received funding from the Minnesota Stormwater Research Council, and the funding came from the Minnesota Clean Water Fund. And I would like to say that I'm indebted, I think we are all indebted to Randy Niepresch and Cliff Eichinger, because they went before the Clean Water Fund many times to talk about how we needed this funding. And that was just a fantastic thing that you did for research in the state of Minnesota. So that's what's happening. Our speaker today is Scott Struck, Dr. Scott Struck. He's been in water resources engineering for 18 years, working for Geosyntec, Tetra Tech, and the EPA at various times. He's active throughout North America. I personally know of projects, and I haven't been paying attention, but I personally know of projects he's had in Los Angeles, Denver, of course, that's where he's from, Minneapolis, Washington, D.C., Calgary, and Alberta. And so he's throughout North America. He's going from project to project. He has a good idea of how projects are done in various parts of the country. And he's going to bring that perspective to us today. Scott has a BS degree from the University of Washington. He subsequently joined the Peace Corps as a volunteer and spent 2.5 years in Tanzania, and then went to Indiana University for 2 MS degrees and a PhD. Scott is also a final, I guess you call him a final reviewer for Engineers Without Borders. So if you're involved with Engineers Without Borders, Scott's a really good person to talk to because he reviews a lot of these things. He rejects some of them. So if you want to do a final review in Engineers Without Borders and you want to get through your final review before they allow it to go ahead, Scott is a good person to talk to get some advice. So it is my pleasure to welcome Dr. Scott Struck.
Thank you, Dr. Gulliver. Well, it's a real pleasure to be here today and an honor because I look at the presenters that have been before me, and there's well-respected professionals there, and I've gotten the opportunity to go back and watch some of those. I watched some of them live when they were happening. I couldn't be in the room with you all here, but just a cadre of outstanding professionals, and so I'm really honored to be included in this seminar series. So, as John said, I've got a experience across the U.S. and a little bit even in Canada and North America. And today I'm pleased to present this project that was done with the city of Calgary. And I also feel privileged to be able to work on this project because the city of Calgary is quite advanced in their understanding of stormwater management, and they're doing a lot of management to try to build on that science. They've built a lot of guidance and so forth. And so, again, I'm privileged to have worked on this project. As well, I am a part of a team and only one member of that team. And so I should recognize my co-authors as a part of this project. And those include Mark Leisingering and Lucas Nguyen from Geosyntec Consultants in the Portland office. Our local consultant in Calgary, David Seeliger with MPE Engineering. And then with the city of Calgary, Michael Ubar and Bert Van Duyn were key members of that team and representing the city. And then finally, Josh Cantone from Optimatics, and I'll get into a little bit more of his role later when I start talking about some of the optimization. So again, just one member of a great group of people to be able to accomplish this project. So in the foreground here in the picture, you see the city of Calgary, another river city, just a lot like Minneapolis, St. Paul. Maybe not quite as big a river, but a beautiful river. And you can see the main one here, which is the Bow River. There's actually one that comes in from the backside of the city and conjoins this river here called the Elbow River. And so again, it's a very river-oriented type of city, similar to ours here. When we look at Calgary, you know, it's really known for being on this juxtaposition of right between the Rocky Mountains, the Canadian Rockies, and the plains. So having the prairies right there. So again, another similarity kind of coming to Minnesota of having the prairies similar to on the western side of the state. Again, butting up against the Rocky Mountains, as well as having incredible national parks there. Anybody been to Banff or the Banff region? Pretty spectacular there, isn't it? It's great, incredible beauty. I got a chance to go through there just before the 1988 Olympics, and I was just astounded by the incredible beauty there. Skiing, I'm coming from Denver, one of my favorite wintertime activities, and so they have excellent skiing up there. I haven't got a chance to ski up there. I can't wait to get the opportunity to do that. Seems like I'm always there in the summertime or fall. Climate, just to give you an idea of the climate there, it is a semi-arid region. So in that regard, it's actually closer to something like Denver, and their precipitation is similar to Denver. We get somewhere 14 plus inches a year, and they get just over 15, almost 16 inches a year. High evapotranspiration rates. And so as we talk about green infrastructure and so forth, this just gives you a little context of how we might think about water removal from those systems and accounting for instance, evapotranspiration. Also, I forgot to mention one of the famous things that Calgary is known for, and that's the Calgary Stampede, of course. Has anybody been to the Calgary Stampede? I have not had the chance to be there for the Stampede itself. I've been there just before, and that town is crazy when the Stampede is gearing up. That and the Flames games are probably one of the biggest draws to the city. So just giving some context of the overall context of this project. It's a pilot study that's combining multiple objectives that the city has. So the city has developed these programs as a part of the management of water resources within Calgary and the Calgary region. A lot of it's based on the capital improvements and long-term planning for this. So in that, they have about 6 programs that are really managing the water resources, and they focus on you know, the major stormwater quality systems, the minor or local stormwater quality systems, community drainage improvements, the asset management, redevelopment of master plans, and of course the guidance. They've spent quite a bit of effort on developing guidance, especially on the green infrastructure and low packet development side of implementation. And all of that's geared towards working towards water quality goals, flood control goals, water supply goals. Again, they're in an area that's semi-arid, so water supply is definitely a consideration for them. Developing robust and effective planning for both short and long term, and then the sustainability of all of those programs. And the idea of this project was to develop a way, using this pilot, to have a scalable methodology to try to incorporate and integrate these programs and be able to apply that in the broader sense for the city of Calgary. So giving you a little more context of the city of Calgary, and specifically the Renfrew neighborhood, it's a low and medium density residential area experiencing significant infill development. Now, what do I mean by infill development? That's that small lot by lot development, not, you know, whole scale redevelopment where we have entire blocks, for instance, being developed. It's really on that lot by lot scale. With that infill development, they're noticing that there's the potential for localized flooding, basement backups, aging infrastructure. These are issues that they're already struggling with in a lot of these areas as they're being redeveloped. And then the receiving water, Nose Creek, is getting greater discharges of suspended sediments and phosphorus. So again, looking at the context, here's our graphic of North America. That's where Calgary is, and that picture actually that I showed you on the title slide was essentially looking at the city from this area right here, which is the Renfrew neighborhood. So if we zoom in on that area, that's the Renfrew neighborhood. That's what we're using as our pilot area. It's about 123 hectares, so roughly about 300 acres in size. And it runs from, as you can see, this kind of escarpment here. Here's Nose Creek down at this end. You can just tell by the switchbacks on this trail that that's a little bit of an escarpment. So we've got a slope going uphill to the neighborhood, which is up here on the top of the escarpment. And really what we modeled and analyzed here was about what's in this picture from this road up to this road here. This is Canada 1, by the way. If anybody's done the Trans-Canada Highway, that's one that goes right across there on the north side of where our pilot area is at. So it's on the north side of the river. Downtown is on the south side of the river, as shown kind of in this middle graphic. But the important part about this particular community is that it's very accessible to downtown. So you can bike there. You can even walk from there. It's probably about a 25, 30-minute walk. But this area is experiencing the redevelopment because it is so close to downtown. It's very commutable via bike. So this is that context of that infill development. We've got a housing stock that's typically the 40s, 50s, even early 60s, look a lot like this for the neighborhoods. And you know, if you go in St. Paul or even places in Minneapolis, this isn't all too that dissimilar from what we see here. So this is what the development's like. You know, you see the front yard, sidewalk coming out to the sidewalk, or the house approaches coming out to the sidewalk. So this is very typical of the Renfrew neighborhood. This is what the infill development looks like. And so this is actually what's happening. I put current because this is an actual built houses there where they've taken those lots that you saw on the previous slide and have either subdivided or built out to complete lot lines. And this is what's going in. So this is definitely changing that environment. The difficult part about it from a policy perspective and a planning perspective is it doesn't often meet, for instance, in the US, we use often a 1 acre, for instance, size threshold before we really have to do a lot of stormwater management on site. So none of these, similar in Calgary, are going to have to do any stormwater management on site because they're a lot by lot development, right? So that's part of the infill development. Now this, of course, is going to create some challenges. So in this process and the project, we really are trying to look out to the future. So we're doing more long-term planning. So what we're using as our time horizon here is 2076. So when we started looking at some of the redevelopment that we've already seen in Renfrew and then projected that forward, we're looking at increases in impervious area where those lots are getting to the order of between 70 and 100%. So the orange here showing, you know, roughly the 70 to 80%, the lighter orange, 60%. And what you can see is that there's a pretty large increase in impervious area as we see these lots redeveloping. So overall, it's greater than 60% projected for 2076. So those are going to have some consequences, of course, on both our drainage infrastructure as well as our stormwater on-site infrastructure. So we're often dealing with these problems that this kind of increase in impervious area is going to create, right? That's, as stormwater managers, we're thinking a lot about this. But now projecting out to 2076, how can we develop tools to be able to try to address this so that it's not going to be a problem in 2076? This is just a graphic showing when we were starting the project, we want to know what were the kinds of problems that were already being reported, for instance, in the area. And you can see that we have some reports, and this is from similar to our 311 calling. These are city reports where we have basement seepages shown in the green stars, sewage backups, and storm sewer backups in this. What I want you to notice with this is that there's not necessarily one place where that's happening. You don't see these centralized in one particular area. They're kind of distributed across the entire Renfrew neighborhood. And the other thing you should notice is that these problems do exist, right? So we do have problems. We do have some localized flooding and so forth happening in certain areas. And so it's not like, even though we're up above Nose Creek there, it's not, you know, widespread and we have a whole lot of them, but they do exist. And so with that increase in impervious area, we don't expect these numbers to go down. We actually expect those numbers to increase. So as a part of the project, we're looking at this, this idea of integrating all of those programs that right now have been really operating in their own program and kind of bringing them together, because we have similar targets in a lot of these programs. And so similar to what we're doing in the US with integrated plans, the idea is that we're bringing both the drainage and supply and all of these and even roads and drainage with our road systems into one framework where we can look at all of those aspects at one time. So with that, we're trying to manage, of course, water quality, which is a major driver. I mentioned the issues with TSS and phosphorus in Nose Creek. We're providing flow and flood control in this system. Again, with that, the increase in impervious area, we know there's going to be challenges in the future. Considering how to improve water supply. We have, of course, our traditional supply mechanisms, but we see that with growth in the future, it's likely that the water supply is going to have greater stressors on it as well. With the redevelopment, we want to be able to develop in a way that's smart and sustainable. And so how do we consider those aspects? Because we know that right now Renfrew is redeveloping, but it's likely a lot of the other areas near the city are going to go through that and experience the same issues with the redevelopment. So targets were developed for those goals. So how can we achieve those goals? We came up with these goals, or the city came up with these goals to no increase in annual average runoff volume from 2015. So that was about about 3¼ inches. This part of this goal here is also a hydromodification goal. So in this, we are really trying to consider not just the overall average runoff, but we're trying to consider when it happens and so forth. So this is a bit of a hydromodification type of metric that we're using. We have a TSS loading goal, which would be similar to, for instance, our TMDLs that we have in the United States, a phosphorus target. And as a part of this, we have their planning level of service that they're trying to get to is a 50-year level of service for the 4-hour storm. So I'll talk about that in a minute about exactly what that means. But that is essentially that what I would call similar to our 10-year level of service that we're looking for our conveyance systems and so forth. So, and then lastly, reducing and eliminate some of that basement flooding. So that previous picture where you saw some of those stars, the idea is to get rid of some of that. So we're kind of incorporating all of these goals that were within those 6 programs that the Water Resources is addressing into one framework and thinking about all of those objectives as a part of this project. So as a part of this, we developed a SWMM model. So we used EPA SWMM for this. And this is looking at the baseline condition model. So you can see the model right here. You know, it's fairly, I'd say it's fairly detailed model. You know, we didn't just lump everything in there into one catchment. You can see that it's really broken down by streets and lots or groups of lots into, I'd say, similar to a block scale or a semi-block scale. So it's a fairly discretized model overall. The other thing I should point out is that they have a dual drainage system. So a lot of times we're representing the surface drainage and into the inlets in one part of the model, and then we have the drainage infrastructure, all the pipes and underground systems in another layer, and we're connecting those at those nodes, the catch basins and so forth. So in that way, we're able to represent some surface treatments differently than our underground treatments. So looking at this, this baseline model, again, we're projecting out for the 2076 built-out condition for this. And I'll show you an example of what that looks like for that 2076 development for the 50-year 4-hour level of service. We also did, by the way, a 50-year continuous simulation where we're trying to tackle the water quality issues. So we didn't want to use just that 50-year event which was intended much more for the drainage infrastructure, and look more at the water quality based on continuous simulation. So when we're looking at that 2076 scenario and trying to turn or evaluate the picture that you see on the left, when we know it's going to look more like the picture on the right. And by the way, one of the things I'll point out on this, which one of the practices that I think is great that the city of Calgary uses, it's called absorbent landscape. And so they're able to actually put their front yards or the yards in general and build a fair bit of soil depth in there and actually collect a lot of water in that. So they call it absorbent landscaping, which I think is an appropriate term. However, that's not always done. That's one of the practices. They don't have to apply those on this lot-based scale. And so you see, even for instance, in this lot here where we have the grass in front, we actually have runoff either from irrigation or an event that's going onto the sidewalk. And so not too dissimilar from what happens in the US when we do infill development. It's likely that developers are compacting that soil and laying the sod right over, and we're not really getting that infiltration capability like you would prefer to have in that absorbent landscape. So In this baseline scenario, the projections are the redevelopment lot runoff increases by 800%. Okay, it's a pretty sizable number. Catchment runoff increases by 190%. TSS loading 160%. And flood damages, which are again localized here, it's really local flood damages, increased from about 12 million to about 90 million net present value. That poses a potential problem. And again, it's our typical mechanisms to be able to deal with this are challenging because our policies don't necessarily regulate at that lot level. So trying to manage this or predict what's going to happen with the system on the left when it starts looking more like the system on the right is really the basis of this project. Okay, so looking at that level of service, this is just an idea of for instance, the 2-year. Here's showing the drainage infrastructure. And to give you an orientation of this particular graphic, the green pipes that are represented here are no surcharge, and then the green nodes or the circles are no gutter flow. So that's everything is hunky-dory. We don't have any problems in that. And then we using this kind of as the stoplight version, the yellow is showing surcharge due to downstream constriction. So now we have surcharges at either the yellow pipe or in the yellow nodes or circles. We have gutter flow due to an inlet restriction. And then the red indicates an undersized pipe in the future. Orange, we have an orange in there for the nodes, gutter flow due to pipe surcharge to surface. And then the red ones show that flooding is over top of curb. So now, for instance, in the model, we're demonstrating that as greater than 6 inches above that rim level, for instance. So again, using the model to look at this, for the 2-year, not too bad. We have some pipes that are shown as undersized and kind of this main stem that goes through there. On the southeast side, we have some red there too. So I'm going to go through this from the 2-year, the 5-year, 10-year, 25, and 50. So we can see how it changes based on those different types of design events. So now here's the 5-year. And I should mention that you'll start seeing these little boxes show up. And those are indicating things like V as a volume loss through an escape route. That means we're getting overland flow outside of the model. So it's escaping out of the system. And then there's a number that's associated with that, which is the meters cubed that it's lost. And then we have a height of the water above the curb, and then a D for duration of flooding. So we're now looking at some of those aspects that are important for understanding our local flooding and the issues. Again, this is with the 2076 build out, but we're calling this the existing condition scenario. So basically, if we do nothing, this is what's projected to happen. Here's the 10-year. We're starting to see a lot more of the pipes that are undersized, and a lot more of the nodes that are starting to have either pipe surcharge issues or flooding over top of curb. There's a 25-year. Now nearly all of our pipes are undersized. And then when we look at the 50-year design storm, now we have all of our pipes undersized for that. And that, again, that's one of our targets for our level of service here. So that's why we're using this as a metric. See all the little boxes that are showing information on the height of the water above curb in centimeters. We have depth or duration of flooding, and then we have a lot of the escape that's coming outside. So that's showing, for instance, the local ponding and the volume that's escaping outside of the system, which we're treating as something that's undesirable because now we have uncontrolled flow leaving our system. All right, so that's the baseline condition. Now, what kinds of things can we do to help manage that in the future? We're looking at gray infrastructure because we know that the pipes are going to be undersized. And there's multiple ways to deal with that. We can upsize the pipe, or we can do storage and delay on the surface. And so, we're looking at things like upsizing pipes, inlet control devices, and you'll hear me say ICDs. What that is just an orifice constriction plate that often goes on the in the catch basin that is slowing the flow down. So it's actually allowing to back up, maybe even to get some ponding above the rim in the street storage, but then slowly releasing it out. So we use that in some places in the US, but not as frequently as they use in Canada. Oftentimes in the US, those are used in combined sewer areas and so forth. Community underground detention storage, again, a frequent practice that we use here. We're putting that in the gray infrastructure. And then paved rear lanes. this was an interesting best management practice, or really a source control measure or stormwater control measure, in that most of their alleys right now are gravel. And with that gravel, if you have a slope, we get a fair bit of TSS loading coming off from those. And so when we started looking at the modeling, we found out that we could do a fair or a substantial amount of reduction in TSS simply by paving rear lanes. Now, it's a little counterintuitive because we're increasing our impervious area, which is something we're trying to counter here, right? But our goal also is to reduce TSS and control the water quality. And so this is one of the ways that, although it's increasing impervious area, we feel like we can manage it, but we can decrease the TSS loading because of paving those rear lanes. So I've put that in the gray infrastructure, although you'll see it in a number of places. The other option is green infrastructure. So we can approach this where we're looking at typical types of source or stormwater control measures like rainwater harvesting, right-of-way bioretention, and community storage even in irrigation. Because remember, we have good evapotranspiration there, and so irrigation can help reduce those volumes as well. Now, I put this suite of practices here. This doesn't mean that they're tied to this. These are just ideas of ways that we can look at it. So it's not that these are necessarily all the practices that they're going to use or the only practices that they're going to use, but these are the ones we're representing in the models to be able to capture how they function. Now, when we design things like this, is this an either or? No, we have to be able to keep that toolbox open. So we also have this hybrid of each of those. And this is where the complexity comes in. We have all of these tools. We have a 300-acre situation, and we want to be able to scale that up into something larger. So our typical approach of doing this is identifying where we can do something and then looking at the practices and going through a prioritization and then coming up and say, okay, we can put this practice there and this practice here. Doing this by hand on a site isn't very hard. You could probably even do it on a 300-acre catchment, and it's a challenge, but maybe still doable by hand. But if you start looking at scaling this up, for instance, to a much larger situation, maybe even the size of the city of Calgary, now we're talking a very difficult thing to do by hand. So, so then we have to think about other approaches for that. So when we're looking at this integrated management, how do we determine how much of each of these to do? Because that's complex, right? We know that these are tools in the toolbox, but we don't necessarily know how much of each one to use. How do we do it where, how do we know where to actually put it? We often say, well, here is a localized flooding issue, and so we need to start here, and then we work out from there. Remember, we're predicting our redevelopment in this, and so we don't always know exactly what it'll be, but we can have these predictions, how much of each to put in each of these locations, and then really, ultimately, how to do this cost effectively. Because that's what's really going to be the biggest issue is how do we pay for this? And that's a huge challenge. And again, something that I think is doable, but by hand is very challenging. So remember, back to our goals, no increase in volume from that 2015 number that I showed you before. We're trying to manage water quality. We're trying to limit and localize street flooding and eliminate basement flooding. And this is the toolbox that we're using to try to do that. Are there other tools? Yes, there are likely other tools that we could do this with, but these are the ones we're starting with and really trying to analyze. And by the way, just these are quite complex. To recognize that this is going to be quite a bit of effort is true. So that's my watch telling me I need to move. All right. So to do this, because of the complexity, use optimization to determine the most cost-effective improvements. And again, going back to that cost-effective part, oftentimes when we're doing this in a traditional approach, we're not necessarily thinking about the costs of each of those practices. We're more thinking about those other goals, like no increase in volume, water quality improvements, things like that. And so that ends up being a layer that we often put on in a later point in that planning. But thinking about it up front is critical. So on the optimization, we use a tool called Optimizer, which has been developed by a company called Optimatics. Josh Cantone, as I mentioned at the beginning, as a part of that company. So we work pretty closely with Optimatics on this. So we often try to keep things in the public domain as much as possible, but we found that their tools are very useful and provide a lot of value. They've been willing to work with us, so we do a lot of coding back and forth where they have their optimization. And basically, this is kind of an optimization wrapper that works around SWM, by the way, or InfoWorks or a number of other models. So it has that capability. But we were able to make those linkages, and they've worked with us to help represent, for instance, a lot of the green infrastructure, because this optimization model was originally developed more on the gray infrastructure type of systems. So for this particular application of Optimizer, what we're doing is we're defining infrastructure. So the goal is we're defining a scenario of what will be used, and how we're going to do this is based on the different objectives. We take that, we run the EPA SWM, we look at volume and load reduction, and we look at costs. So for the SWM, we're looking at the hydraulic performance results, and then we look at the volume and load reduction. So now we're looking at water quality performance, and then we have to look at the improvement costs. We take that and we look at what's called a total scenario fitness in Optimizer. And by the way, what if you don't meet that objective? Is that okay or is that not? I'll get into a little bit more of that, but that's called a penalty cost. So for instance, if you're not meeting your objective, you might get charged a penalty for that. And so that's the way we look at the total fitness, which ends up looking like a total cost for each of these aspects. And that's how we evaluate whether the scenario is good or not in the optimization framework. So real quick, these are the general approaches for the simulation. I'm not going to go into detail, but just to say we're really defining those objectives, which I've kind of presented to you. Defining decisions, I'm going to go over a matrix of what those look like. And then we're selecting improvement scenarios, evaluating the different decisions that are going into this, and then finding the best solution. And now I've used the term optimization. Here I'm calling best solution. And so when I talk about the solutions that we're getting, I'm going to call those near optimal, because I don't necessarily like the term of optimal, because we don't necessarily know what optimal is. I'll call them near optimal. So bear with me on that. So the different scenarios that we looked at. So we have the, and this is really what we use for our matrix here. We have our planning criteria. Those look like, we can upsize pipes. We can use inlet control devices. We can use community storage. We're looking at bioretention, right-of-way bioretention, on-lot cisterns. And in this, we looked at both on-lot cisterns from an individual lot or versus grouping them on a larger scale as a way. So that's the group or independent. And then we have our design criteria that I pointed out. We have street flooding. So that was one of our criteria. We have system overflow. So is it leaving our catchments that we want to control? Junction freeboard. So that now we're looking at our depth at each of those nodes. Peak discharge, annual volume, TSS load, annual, and we have a hard target and a soft target. So annual volume, hard target, and TSS load, hard target, and then all of those, both of those two in a soft target. Now, what do I mean by hard target and soft target? Because this is actually quite important. And by the way, you can see the different matrix here of what we included in each of these. And up at the top, we have pipes and ICDs. So that's mostly the gray infrastructure. Pipes, ICDs, and community storage. Now we put some community practices, and that can be mostly gray storage, but we can have surface community storage. So that can include a little bit of green storage. So those are the twos. When you see any of the three scenarios, those are essentially our green infrastructure or stormwater control measures only. So that scenario 3 is essentially saying we're only going to take the approach where we use green infrastructure to manage those issues that we have and to try to meet these design criteria. And then the scenario 4, and we did six of those are all the hybrid potential scenarios. So now real quick, back to the annual volume or the hard target and soft target. So we're using costs in a lot of this, and I'll show you what those cost curves look like in just a second. But when we're looking at optimization, if we use a hard target, what we're saying is that if you have an objective, you must meet it. So if you have, let me think of an example. If you have a TSS, what's your phosphorus threshold, John, that you guys use? Or 60 100 milligrams per liter? 60 micrograms per liter. Okay, that's what I thought it was. So if you have to meet 60 micrograms per liter, okay, if you have to meet that, you would set that as a hard target. And so what that looks like from a cost optimization perspective, if you say, there's some cost to meet this, but if we don't, remember I talked about those penalty costs? If we don't meet 60 micrograms per liter, we have a very high cost. So, and it doesn't have to necessarily be a real cost. We could say $1 million, okay? Because it doesn't really matter. What it's really doing is it's saying on the optimization side, because it's trying to do the least cost scenario, it's going to say, if that's going to cost $1 million for me to have anything over this, I'm going to avoid that. So it says that's an unrealistic scenario. So that's what a hard cost is. It basically says, you must meet this, so let's avoid doing anything above it. So the other way that you can approach this from an optimization perspective is to put a soft cost on there. What if we say it only costs $10,000 or $100? And so now you're saying, well, we don't have to meet 60 micrograms per liter at this point. We know that's a big system, but we want to do as best we can. And so we want to keep that minimal, but we also want to minimize cost. So it's recognizing that not all solutions have to meet this exact target, that we can have some flexibility around that. And that what we'll do is we'll actually try to optimize those costs, keeping it as low as possible, but not necessarily at that 60 micrograms per liter, but maybe it's a little bit more. And you can even, by the way, incentivize it where you get negative costs. You can have a negative penalty cost if you really want to incentivize things that do much better than 60 micrograms per liter. Does that make sense? So that's a little bit of the economics and how this hard target and soft targets work. And so we applied those both to annual volume and TSS load to be able to look at and see how those vary. Again, we looked at those primarily at the hybrid scenarios. All right. So I mentioned I would go over a little bit of the costs, but a part of this as well, we need to have performance costs. So we need to know how well those systems are doing. How well are they doing for our water quality? How well are they doing for our volume control? And so this is kind of some of the information, for instance, that went in there. You can see some bioretention performance there. We have volume treated by the bioretention. We have load reductions. And the other one I'll explain here is the city of Calgary and other places often use this. We kind of use this too, but they call it the I to P ratio. So that's an impervious to pervious ratio. And the impervious, of course, is our drainage area and what our effective impervious is coming from that. The pervious ratio is actually our footprint of whatever we have. So for instance, for bioretention, it's that footprint that it has that we're calling pervious. So what it essentially is our ratio of drainage area to our practice area. Simple as that. And so, you know, if we're in the I to P ratio of 10, we're talking about, you know, that practice is the size of the footprint is about 10% of the drainage area. And we go all the way up to 40% on that, or a ratio of 40 I to P. We also looked at different aspects of infiltration. So we looked at 2 millimeters an hour, 5 millimeters an hour, and 10 millimeters an hour. We actually ultimately ended up using 2 millimeters an hour to be conservative, but we wanted to understand what that change would have on our optimization process. I have some land use categories for the types of the TSS runoff from each of those. Notice unpaved alley, 1,200 milligrams per liter. As I'd mentioned before, one of our practices that we use is paving the rear alleys. So it's really trying to get a reduction in that. Here's some of the cost data. And again, some examples here. So we have underground storage costs. We have surface storage costs. And by the way, this one, because that size of practice is so specific, we actually said, okay, it can only go in this location. So when we're doing the modeling of that, we had identified 3 locations throughout the catchment where we'd say, this is the only place where this can go. But now we're including that as a potential storage node in there. And so we're seeing what that will have, what kind of effect that will have through the optimization process. Right-of-way bioretention on that underground storage. By the way, we did cisterns for both underground and above ground storage. And by the way, we represented those cisterns as both a retention component and a detention component. A retention component as a reuse. So we said there's so much reuse each time. We want to try to have a part that we're maintaining within the cistern to be able to have available for instance, in-house use or irrigation. And then a detention component where we just control that more based on orifice flow, where it would store it more for that peak flow control and then release it over time. Surface property flooding, so we have some costs for that. So if it gets up above a certain level, we start having higher costs. And then freeboard penalty per manhole. So this is where when we get over a certain amount, now we're starting to get flooding of cars, for instance, that are parked on the street. And then our costs increase substantially from that. Again, based on the freeboard of those. So I mentioned that fitness solution is how we're evaluating this. And this is, for instance, an output of what the optimization looks like. And what you see on the far left side of this graphic is that it starts out with a scenario, right? Or a number of those different components. And it's trying to meet a certain objective. And it starts out with an idea. Okay, we'll put this many of this many of this, and then it starts evaluating that. And it comes up with an answer, and then it says, well, okay, is that a good answer or not? Well, we don't know. We need to have it compared to the next one. So it runs it again, and it changes one of those. And then it gets an answer and says, well, can we improve upon that? Is that better or worse? If better, well, let's see, can we improve on that? And it does another iteration. And so this is the process that goes through. And you can speed this up, by the way, by seeding it, by giving it a scenario to start with. So oftentimes you can speed it up. But what I'll show here is that when we look at the axis at the bottom, this is the number of evaluations. And you'll notice when we start getting down here at this part where you start getting kind of asymptotic, we're up at 40,000 evaluations. Now, remember when I said this is hard to do by hand? Can you imagine doing 40,000 evaluations by hand? And by the way, this is one of the easier ones that we did. This is one of the simpler models that we did earlier. So for instance, we just had a few changes. And so we had some that were over 400,000 evaluations that it looked at total. So part of the optimization is to be able to look at all these potential different solutions and understand what that means. And so you can see that, that even in this example here, it made some decisions. It seeded it, or it started with a part. It actually started to decrease, and then it tried a couple other things and then increased it. And the blue line, by the way, is kind of the sum of all of these. And so obviously what it's doing here with this accuracy as currency on this side, it's trying to find the lowest cost solutions that are meeting that. And so we're calling that as a near optimal. We find what it is, and that's our lowest cost. So near optimal solution. Now we use this approach to be able to define those scenarios that meet those objectives. So I gave you that matrix that had all of those objectives. We actually ran it 17 different times looking at those. And by the way, there's a whole bunch of other ones in between that we were kind of trying to define the scenario. Well, should it be this, that? So what does that look like? So just to now give that more of a picture here. So now I'm looking at scenario 1B. And this was primarily inlet control devices and storm sewer upgrades. So we're looking at that, just increasing pipe size and just putting in those inlet control devices within our catch basin. So I've shown that kind of through this image here. I'm calling this a gray infrastructure. Maybe hard to tell, but this is a gray box here. So we're putting our inlet control devices to restrict flow, and we're upsizing our pipes. The red there is showing the increase in that pipe size from the black. And so that's one of our tools that we have in our toolbox. We want to understand how that works. So we went through and did that, and we have some results. And so I'm going to go through the next 6-8 slides are going to look like this, where we're looking at what the scenario is to define it, and then we're looking at the results. And by the way, it has a graphic over here that's showing what the improvement decisions look like in terms of pipes and nodes for the ICDs. So this one's showing the number of ICDs and the pipe upgrades. And then we have some cost evaluations in this because that's a part of this as well. And by the way, I've included, at least in this, the baseline. So that 2076 condition, the do nothing condition. And this is what we were getting. We were getting with that baseline condition for catch basins with max depth greater than 0.2 meters, we were having 55 of those, so that's a number. Manholes with less than 1.2 freeboard, and by the way, the freeboard, so it's measuring from the bottom to the top, so so reducing those is better. So the baseline was 136, we have 83. So if we look at this, we've improved on our catch basin depth, right? For our number of systems that have that catch basin depth or that are lower than that. For manholes, we've improved on that. We went from 136 in that baseline condition to 83. In the next one, 50-year design storm overflow volumes, we went down from over 2 million liters down to a nominal 600 liters. That I would call that pretty close to zero as far as modeling is concerned. For our peak discharge, we went from 5.2 to 9.9. Wait a minute, that's up. We increased that. Why? What were our tools? We increased pipe size. Did we slow down velocity? Yeah, we put ICDs on, but we now have larger pipes. And so we've actually resulted in an increase in our peak discharge. Is that counter to one of our goals? Yes. So that's not good. So I have a red X for that. Annual discharge volume, same, because why? Did we do any volume reduction in that? No, we slowed it down, but our mass balance is the same for the volume that went in and the volume that came out. So that's the same. And our TSS loading didn't change. Now, would we probably get some settling in that because we have ICDs and in the catch basin, we'd get some settling in there? Yes, that's likely. But overall, this a conservative model, we didn't really have any loss. So that's also the same. Okay, so now let's look at scenario 2B. where we're using regional storage and storm sewer upgrades. Okay, need to finish up in here. All right, so these results, I'll just go over this quickly. We did improve on the 50-year design storm. Now I'm just going to go to the kind of these four main metrics that we're looking at instead of looking at all of these. We didn't help on the peak discharge. Again, we increased our discharge. We're about the same, again, for our average annual discharge volume and TS loading, we're the same. So we're not really meeting our objectives. We're essentially staying the same as a baseline on those last two. And again, this is the graphics there and here are showing what those results actually look like physically within Renfrew for those pipe upgrades and what both what the upgrades are, the improvement decisions, and then the results, the performance results in the lower right. And so let's go on to the next scenario. So now we're looking at scenario 3C. So this is a green infrastructure only scenario. And now we're putting in the paving the rear lanes. We've got rainwater harvesting, and it's being used indoors. We've got these bioretention tree trenches along the right of way. And so these are all of our practices that we're using. Notice we're not upsizing any pipes. And so we're basically using only a green approach for this, other than perhaps maybe the paved rear alleys, but that's helping us on the TSS side of things. So let's look at those results. It says 2B. This should be 3D here. But what do? We get we could do a substantial improvement now in our design storm overflow volume, because now we have what? We have bioretention. We have things that are slowing it. We have use. So we have a lot of volume losses in the system. And so we've improved on that. We've improved on our 50-year peak discharge. So that's decreased. And the average annual discharge volume, 90. And then the TSS loading has substantially decreased as well. Now, the one thing I haven't been pointing out on these, and I probably should go back and point those out, is the cost. Did anybody notice the cost on that first scenario? About 20 million. How about the second scenario? About 20 million. Now, those weren't really necessarily meeting our objectives. Now, what's the cost on this one? Almost 40 million. So we've now substantially increased. Now, we're meeting our objectives, but at what? At a cost, right? So now we're at 38 million. So let's now look at the hybrid scenario. And now we're kind of basically throwing everything in there. You know, we're looking at all of this stuff. And this is, I can't remember, I think this is going to be, might say if it's 4, I think it's 4D that we're looking at. It might be 4A. So I'm not necessarily going to the hard soft cost on this, but this is basically everything. If we put everything in there that's available for us to use, what does that look like? And what you might notice from just even simply looking at this graphic and this graphic is we don't have very many problems. We've upsized pipes, so we don't have flow problems and so forth. And we've got all of these, we've got management in a lot of the places. A lot of them are the right of the bioretention. So that's what these colors here along the right of way there, or the streets is a bioretention. And we've reported it, by the way, as an I to P ratio. We've got some cisterns in places. We've got the ICDs. And what do we notice for our performance results? Okay, we have nominal flow, overflow volume now. We've got maybe the same for 50-year peak discharge, but this is actually near our target anyway. And then we have average annual volume that's maybe not quite as good, but it's not too far off from the green scenario, right? Which we said was a substantial improvement. And then we got relatively similar loading for TSS. Okay, so not too far off from it. A little bit above it, but maybe not quite the same as the green infrastructure. What do we notice about the cost? We went down to 32 million. So we've got a 6 million savings from looking at a hybrid approach. Now, is it more than the 20? Yes. But did the 20 meet our objectives? No. So this is getting more towards our idea of something that meets our objectives and is cost efficient. So it's on that least cost side of things. So, all right. So the last part I want to talk about this, and I'm getting short on time, but I'm gonna kind of zoom through this a little bit, is the triple bottom line aspects. And these are the kinds of things that we looked at for triple bottom line, everything from health benefits, construction impacts for more of the social side. We did look at life cycle costs. We looked at flood reduction benefits. We looked at property value enhancements. And then for the environmental, we used some of the same things that we looked at overall, providing some values for those for the water quality, volume peak flow reduction, water use. So now a supply exchange, construction impacts, air quality impacts, things like that. So I'm going to show you this graphic here, and I know it's way too small for you to read, but what I want to do to talk about this, the types of data that we used, and this is, by the way, the spreadsheet that went into our triple bottom line analysis. What I'd like to point out is that the values are based on real and local data. So there's a number of tools out there that do triple bottom line. Oftentimes, they're not necessarily tailored to the local environment where you're doing it. And so you'll notice a lot of this stuff, they might have Calgary numbers or City of Calgary. And by the way, City of Calgary does have a TBL tool. We took some of those things. We didn't take them all. And because the biggest challenge was, for me, as an engineer and a scientist, I want this to be something that is well supported by science, that I can give it to any academic, I can give it to anybody else, and they'll take it and say, yes, well supported, check that box, because, and by the way, transparent. So I want it to be transparent. I don't want these numbers to be hidden by anybody. I want them to be out there to say, oh, okay, is that a value good or bad? And I'm not saying that all these values are great. I'm saying that's what the literature said. And so we're using those and trying to tailor them as much as we can, both to Canada and even more so to Calgary, or Alberta and then Calgary. So, so these are some of the calculated variables that we use, and it includes things like design life, current year, all the inflation. Those are the typical ones we use, but it has things like local streets and an average daily traffic volume, CO2 produced from idling. So a lot of our construction kind of impacts that we see from that. Then we have area-specific variables. Again, the point is that this is documenting as much information as we can that's local to Calgary or Alberta and so forth. And so we had this kind of prioritization of the type of information we use. Is it North America? Is it Canada? Is it Alberta? Is it Calgary? And that last one, the fourth one, is really our highest priority data. So again, we use this. Values are as much as we can based on real and local data. Real data, by the way, that's the other part of it too. It's real data. We didn't model it. We didn't pull it out of the air from somewhere else. And I feel like that's important for our tools. Then we took all of that, and when we're looking at them, and we actually did a sensitivity analysis. And what we did is we added a little bit to it. We subtracted a little bit from it and said, how much does our answer change when we do this TBL? Because that's important. If you know the sensitive variables, it's not that you necessarily are going to not include the insensitive variables. Maybe there's a reason that you want to include those, but we really want to know the variables that are dominating the decisions in this. And so in this inflation rate, you might expect that makes a lot of sense when you're looking at a TBL over long-term long time frame, that inflation rate will matter. Discount rate similarly will matter. Design life, that was very sensitive. So if the practice lasts 15 years, 30 years, 75 years, things like that, that's important. Property value we found to be quite sensitive. And in this, by the way, the property value, because we didn't have enough green infrastructure, and if you look at the actual numbers there, it says adjacent to green infrastructure and or open space, and not adjacent to green infrastructure and open space. And we took, they actually have a pretty robust, not quite like Zillow, it's actually better than Zillow, with near market prices. And we looked at about 100 of properties that were, it was actually 120 that were not adjacent to green infrastructure or open space. And because we don't have enough green infrastructure, we had to include the open space. And then we did about 60 that were near or overlooking open space or green infrastructure, and came up with those values. We found that was a sense of value, but we felt like getting a large enough population, we would be able to get some of that variation. And we did notice a difference, by the way, between those. But it is a sensitive variable. And then volume reduction benefit to Nose Creek was also sensitive. So I want to go over kind of the scenario comparison. So we developed those comparisons, those scenarios using the optimization framework. And now we're comparing those using a triple bottom line approach. We're comparing scenarios that were developed in optimization, now using TBL. The thing I'll point out here is these are relative values. So we do have a benefits and we have a cost in Canadian dollars in 2018. That's not meant to program how much each of these scenarios is going to cost. It's really intended to provide a relative difference between each of the scenarios. So I think that's very critical that people understand that these are for comparison's sake. And oftentimes the best tool of TBL, in my opinion, is for conveying this kind of information of what is the difference between the scenarios when we look at these broader scope of potential objectives. It's not for programming dollars. It's not for determining the actual lives saved or anything like that. It's more for comparing your different scenarios. And when you see this overall, we see the 3C, 3D, 4A, 4D, 4F are kind of dominated, and those are the hybrid ones in the 4s, the green infrastructure on the 3s, and the gray infrastructure in the ones. So, and then the baseline condition that had the cost of the flooding and so forth. I mentioned those at the beginning. These are all the different things we looked at in that, and you can see the different values of those. So now I'll use a metric that's often used with triple bottom line analysis, and that's our benefit cost ratio. And what I'll say is that benefit cost ratio can be used in multiple ways. And you have to actually know what it's referring to when you look at these. So one way to look at benefit cost ratio is to look at all of our scenarios versus the baseline condition. So this is the baseline condition over here. So we're comparing these, and we can compare those, and that's what these values are here. The other way to do that is to compare each scenario versus, or actually the scenario within the scenario itself, the benefits versus the costs. And so that's looking at the value of each individual scenario, but not between scenarios. And that's what this is. So the BC versus 2076 is showing it versus the baseline condition. The BC versus just the BC numbers are now showing what's the benefit for doing that particular project versus the costs for doing that particular project. I'll show you what that difference can mean. So let's choose 3C really quick here to look. That's our best BC 2076. And by the way, it's our best BC, our benefit cost ratio overall with the 3.02 and the 4.93 respectively. And so when we look at this, that's good. That's good. It's the best in terms of the whole crowd there for our benefit cost ratio. Now let's look at 4F. 4F is not as good as scenario 3C when we look at BC 2076. But when we look at just comparing the benefits versus the cost in that particular project, it's actually quite high. Not quite as high as 3C, but by the way, better than any other one when you're just comparing the benefit costs. Now, why might we want to choose 4F over 3C? Well, maybe we don't have that $38 million that it costs or something like that. And again, relative terms. But what's more important about this one is that maybe we have a limited outlay of costs here, but we get fairly substantial benefits. So if we have minimum dollars to spend, which you can see the bar below the center dash line there, which is what it costs to do it, is smaller. So if we have a limited amount of dollars to spend, we actually get pretty good benefits. So if we don't have the dollars to be able to do 3C and get those great benefits that it provides, we can still do 4F because we have a limited number of dollars. Now, is that reality? That's reality. And so by providing this in a different way and looking at these different benefit cost ratios, we get a better understanding of the types of solutions that we might be able to choose from. So with that, conclusions, stormwater infrastructure planning is getting increasingly more difficult. Multi-objective parameters that we're looking at all kinds of different flooding, water quality, growth, all of these kinds of things are now coming into play. Incorporating network systems and effects is critical. Being able to understand that underground infrastructure, the above ground infrastructure, those are all critical pieces of this. Too many decisions to be able to make in my head. You guys are capable of doing it. And so using things like optimization software are going to be a part of what we do in the future. Marcus talked about technology increases. I think this is one of the technology increases that we're going to see as well. Using triple bottom line, great decision support too. It's really, I think it's as much for communicating to decision makers, et cetera, the differences between the scenarios. We're looking at more holistic types of benefits and costs. Again, that's more for a communication tool more than anything. Don't program your dollars on it, things like that. And it provides justification for doing that particular project. So with that, I'd like to conclude and I'd welcome any questions.
Okay, let's thank Scott. So what questions do you have for him?
Thanks, Scott. A couple specific questions to your project. Were there any restrictions on green infrastructure practices such as soil permeability or that? And did you account for potential changes in rainfall patterns in your modeling?
Good questions, Mike. So there were restrictions. So for instance, on our right-of-way, we assumed a certain footprint that was necessary for each bioretention. And then we did things like put a single, we did put trees in there, by the way, which added a lot to our health benefits. And I think it's a good practice. Now, I know that that presentations have said, you know, as long as you manage that, manage the leaves and so forth as a part of the management of the systems, and I do agree that that's completely important. So yes, there were a lot of restrictions on things like how many can we fit in here? Is it realistic? We did end up going with a limited infiltration rate, and that was actually based on, even though we did field testing within the Renfrew neighborhood at a water services department employee's house in his front yard, we did some testing. We didn't use that rate. We actually went with a more conservative rate. So you notice we looked at, I think it was 2, 5, and 8 millimeters per hour, and we ended up using the 2 in that modeling just to be conservative on that, because variability, everything else that goes along with that infiltration. So did I answer your question in terms of, those were some of the restrictions? Are there other restrictions that you were thinking about? Oh, and the climate question, great question. So we were going to tackle that. We weren't able to do it within this budget, and so we proposed another add-on to this that was actually looking at climate change in the region, and then add that into this too. So we would go away from necessarily, or change the design events that we looked at that I showed before, the 2, 5, 10, 25, and 50, and look at something that was more included with climate change variation. That has not been done yet.
So my impression of Canada is that they don't have some of the regulatory constraints that we have, MS4 permits, TMDL requirements and such. In a US setting, would you incorporate those into this optimization, and would they both mostly be cost in the cases where you weren't able to meet regulatory standards?
It's an interesting question, Randy. So you did notice that we did have both loading and for instance, a phosphorus requirement that we set. Now that wasn't a regulatory set number, but it was a desirable target anyway. So it was treated very much like a discharge concentration or a loading rate. So I would say in many ways, that's like looking at a TMDL, for instance, on your receiving water. And so we were trying to do that as a part of this. And so yes, there's definitely the capability to do that. On your point of no MS4 permits, they don't have MS4 permits, but they still have these water quality goals. And so it is, yes, it's different, then it doesn't translate quite the same. Now back to the flip side is, how would this change if we were doing this in the States? I don't think that the analysis would change much. Again, most of you might have a TMDL. It's going to be assigned to, for instance, all of the MS4 in that area. And so each of those discharges are still going to be just the same as this. Fortunately, in this, it was fairly simple. We had one discharge that we were really representing. You would have to make that certainly much more complex to include all the discharges. But it would, I think, be done very similar manner. How would that affect the costs? It would just be more complex, again, where you have the potential to upsize pipes and downsize pipes and so forth in different manners to get all those discharges. One other point I'll make really quick from the optimization and looking at those pipes, it was interesting. We did 2 approaches. We did, I would call a non-engineering approach, which was we just let the optimization go through its process. And looking at the results, what we found is that it would upsize some pipes and then leave some pipes further downstream small, which seems counterintuitive, but what it's really saying is that we need storage in this, and we're using that smaller pipe as that constriction in that smaller pipe as a way to delay that storage and to store it there and to bring it in. So even doing it in that kind of situation, it tells you things when you're getting that optimal results and you go, oh, okay, we actually need more storage in this area, and I can see about where it needs to be within the watershed. And so that kind of analysis is informative. But then we also ran it and said, okay, the tool needs to say, if we size this one to X, this one needs to be X plus something, because in general engineering approach is to upsize everything else downstream from that pipe segment. So that was an interesting feature that came out of this. That could potentially happen as well. Or we look at a new approach where we start using pipe storage, which, by the way, combined sewer systems use all the time and do that quite a bit. So maybe that becomes a new part of our tool set, is to actually do a little more pipe storage with our gray infrastructure.
We have a question from the online audience.
So the question is, when you were evaluating the cost effectiveness of the different scenarios, did you in any way consider the difference of cost borne privately versus publicly?
Ah, that's a fantastic question and a very sticky one because, so the short answer is no. Right now we were just saying an overall cost because right now we wanted to understand what would be the best approach. Now that approach, which I think starts getting it more into that policy side of things, and I had alluded to some policy challenges. So who bears that cost is important, certainly. And so if we're doing things on site, on a person's home, putting cisterns in, things like that, now that becomes borne by the developer and or the homeowner, right? And so that is a different situation. And that's why perhaps that might be an approach that they say that's not palatable. And so we want to not do on-site collection, and we'll just stick with other opportunities, our right-of-way bioretention and things like that. So we didn't necessarily consider that, but that needs to be considered overall. Plus, it also affects your policies that you put into place. If you are going to do something like that, how do you control things like, well, this part of the neighborhood said it needed a 3,000 liter tank, and this one only needed a 300 liter tank. So now you have an inequality of there, and that gets very difficult to implement. Oftentimes to solve that, we just put a blanket policy and everybody has to put in an X size tank or something like that. And it might be an average of all of those. So that's where we start getting into the tools that actually implement these, and that's on the policy side. That gets much more challenging, and we didn't really do much of that.
Okay, I'll give myself the last question. What did you assume for infiltration through green infrastructure? Did you have any infiltration rates?
We did, and I don't remember those right offhand, John. So we had the 2 millimeters per hour was going into the native soils. And I don't remember exactly what we had going through the green infrastructure. So I'm sorry.
2 millimeters per hour is what you assume from the native soils then?
From the native soils, correct.
That's type C or type D soil?
Yeah, it was probably type C. In some places there might be a type B. I think when we actually did the testing, we were getting somewhere between 8 and 16 millimeters per hour. That was done in the fall, I think of 2016 or 2017 when they did that. So just relating temperature and when that was done. So I don't exactly remember what we used for the media itself, for instance, within the bioretention cells. So.
Okay, let's thank Scott again.
Very good. Welcome back to our panel discussion for the Minnesota Stormwater Seminar Series. My name is Andy Erickson. I will operate as the moderator for the panel. I will introduce our panelists, give them a moment to describe their relation to this topic today. And then I will ask actually some specific questions to get the discussion started, and then we will open it up for questions to the audience, both the online audience and the in-person audience here today. So to start, I'm going to start here next to me with Brett Emmons, who is the CEO of Emmons and Olivier Resources here, currently in Oakdale, but soon to be in the Midway area of the Minneapolis-St. Paul metropolitan area. So Brett, what is your relation to this topic?
We do a lot of analysis and planning for communities all the way through design. So being kind of a practitioner on this, bring that lens to it as a design engineer. And I think what's interesting is it's both exciting that there are so many new tools out there in LID, but as well put by Scott, it also then becomes quickly confounding which ones to choose. So we've done some work in Inver Grove Heights and a zero discharge system that we've helped develop. Argenta Hills was one of the very first developments that occurred there, and we were part of the design team. And in a way, it was fun because we were able to pick out a whole host of LID BMPs along with some gray infrastructure and came up with a zero discharge system that added amenities to the site. And through that exercise, we used different tools depending on the location. But as you start to scale up, we've also set up a framework for that whole entire area of Inver Grove Heights to also be zero discharge. But at that point, it is going to be site by site where folks are going to have to take that framework that's been established and then apply their design skills. And I think as we've seen that, it's been pretty successful so far. But as you do see designers come forward with developers that are struggling with that, they're used to doing kind of putting in a pond, and now you're opening up to new ideas, and they sometimes kind of take a try or two at it before they end up with a hybrid. We've seen reuse come up because they still can use a pond, and that's become a very popular one that really just keeps happening over and over again. I see a lot of. The last one I can think of is, and those are both new development. So I think that is a different world than what Scott was talking about, which is redevelopment, what some communities deal with. We happen to have done a project similar to what Scott was describing in Edmonton, also in Alberta in Western Canada, where we're looking at the fully developed portion of the city, went through an automated siting process of 80,000 some BMPs. So again, at a bigger scale. And I think the takeaway from that was I don't know that we have the exact right answer, but I think what we did was we did give the community a marker to say, well, you can use green infrastructure. These are the benefits, quantify what % of their solution, their goals they can meet with that, because that was important to them before they even wanted to head down that path. These are the kind of costs that you would expect, and if those are reasonable or not, and they felt like they were reasonable. So I know that as time goes on, it's going to evolve what the actual BMP is on that site, but we were able to give them a good, I think he called it kind of the seeded scenario. We gave them a good start of where we think it could be and how it could turn into something that really does provide an economic benefit to the community. And I think it's that space making. I think that's what also keeps coming up as something kind of an unexpected surprise for people, is how much this can actually add to the community in that kind of triple bottom line way.
Great. Thank you, Brett. Our next panelist is Doug Snyder, who is the Executive Director for the Mississippi Watershed Management Organization. Doug, how do you relate to this topic?
So for us, we work in a watershed that is a pipe shed, essentially. We don't have surface water in the sense that a lot of watersheds manage to small streams or for lakes. And as we look at those systems, for us to try to optimize how the work we do in water quality, water quantity, or habitat, is we have to look at the various systems that we're trying to manage. So those pipe systems, and then how those overlay with all the other urban systems that are within our watershed. So we're looking at transportation, park systems, all those adjacencies that we have to deal with. And as we enter into our 10-year comp plan this year, what we'll be doing is taking all the data that we've created over the last 6-7 years and putting those things together, starting to overlay those and trying to find the opportunities within the watershed, or those sub pipe sheds, if you will, where we can do the most good, excuse me, for that system, as from a system perspective. We're non-regulatory. Our cities do the regulatory work on a lot by lot basis, but we feel like we can fit in from the watershed basis of doing kind of district scale or regional scale, if you will. So anything from 10 to 20 acre district kind of systems to looking at several square miles at one time, and then saying, what do we do with this in order to optimize or to improve that existing system that's in place to meet those water quality, quantity, and habitat goals that we have.
That's great. Thank you, Doug. Our next panelist is Wes Saunders-Pearce, who is the Water Resources Coordinator for the City of St. Paul. Wes, how do you relate to this topic?
Well, I really found Scott's topic fascinating. I think what's going on in the Renfrew neighborhood is really quite interesting. And in St. Paul, we also have a lot of infill development. We have over 50,000 single-family residential properties in our community. And so these incremental changes in the landscape are something that I pay a lot of attention to. And how does that impact our water resources? But for St. Paul, we're a fully separated community. And lately, the way that we've been relating to this topic in our experience is, how do we use rain as a resource? And what I mean by that is, how do we be more intentional about managing stormwater to get multiple benefits? And one of the things that we know, because we've been operating under a program of stormwater requirements for decades, for rate control, and then more recently for water quality, we know that most of the time in our dense community, we're fully developed. So most of the time people are putting stormwater management practices underground. And while we're looking to optimize, while we're looking to really gain these multiple benefits, how do we do that? How do we demonstrate the value of stormwater management in a way that's more than just one dimension? So specifically in St. Paul, about 85% of the time, stormwater management is being done underground, partly because we are a fully developed community and these infill practices really restrict how much opportunity you have. And similar to my colleague Doug, we also are moving towards thinking about more district-based approaches where we can be a little bit more targeted in what we're trying to accomplish for the value of stormwater management as a system-based asset. So we're getting those co-benefits, those multiple benefits. So we're really looking at ways to do that, partly through the modeling exercises that Scott talked about, but partly also just through changing the way we view the way stormwater management should be deployed, whether it's underground or on the surface.
Great, that's great. Thank you, Wes. So we just heard Scott give his relation to this topic. He kind of set the groundwork. What I'd like to do is actually come back through the panel again and ask a little more detailed questions. So for example, for Wes, if we go back to Wes right away, we have the Ford site, which many of us in the room are familiar with. Maybe some of our online audience are also familiar with the Ford site. And that's kind of a very unique opportunity, right? And I'd like to hear kind of how the City of St. Paul worked with partners and what you did in planning for the Ford site that kind of fits into this whole context and how it kind of, you know, relates and parallels what we've seen with Scott's talk in that example.
Yeah, absolutely. And the Ford site in St. Paul is one of those once in a generation opportunities, partly because of its scale. It's a 120-acre area where the Ford Motor Company had an assembly plant for almost a century. And the Ford Motor Plant closed in 2011. And since then, the whole site has been cleared of all structures and all imperviousness. And it's ready for redevelopment. So during the time that it was closed and the site was demolished, the city and its partners were really looking to inform our master planning process, knowing that there was going to be stormwater requirements to meet, but how do we do that in a way that's more strategic? One of the things with the Ford site is, number one, it drains directly to the Mississippi River, but more importantly, it also drains to an intermediate creek, the Hidden Falls Creek, between the site and the Mississippi River. So there's a receiving water downstream of the Ford site that we wanted to protect, as well as the receiving water of the Mississippi River, where we want to protect water quality. And what we were trying to accomplish was looking at a paradigm that helped us move away from our traditional approach, which I just mentioned. Most of the time when people are managing stormwater, when developers are managing stormwater, they're doing it on a project by project basis, on a parcel by parcel basis, and they're doing it underground. So what we wanted to do was really set the foundation to inform our master plan, where we can be more strategic and develop more of a district-based approach, where we're sharing stormwater management throughout that whole 120-acre development site, doing it in a way that not only meets the water quality goals for the Mississippi River, but also really ratcheting down, or in another, saying it in a different way, going above and beyond the standards so that we can restore the Hidden Falls Creek that's immediately off-site downstream from the Ford site. So this district approach, really what we wanted to do is an analysis similar to Scott and Calgary, where we're comparing a baseline alternative with these more ideal scenarios. And we did that using software very similar to what Scott described. And the baseline scenario really was looking at underground stormwater management done on a parcel by parcel basis. And this other alternative where we were bringing that amenity to the surface, using rain as a resource, and actually recreating that Hidden Falls Creek on the Ford site, and designing green infrastructure in a way that allowed all the development to be serviced by essentially one centralized system, and capturing the co-benefits, so the air quality benefits, the heat island reduction, as well as the water quality benefits, the recreational benefits, all of these amenities from this higher performing system. Because partly we knew that it would also entail more maintenance costs. So we wanted to be able to compare the alternatives, not only between this baseline and our ideal scenario, but include the analysis of the capital costs and maintenance costs, and in totality, be able to say, what's the benefit to cost ratio between these approaches? And, you know, I think Scott did a great job of describing how you can move through that assessment. We ultimately found that the benefit to cost ratio is much stronger with in a system that was a district-based system using rain as a resource, where we had this centralized system that was recreating this Hidden Falls Creek and serving as a green infrastructure system. And because of that, we were able to include that non-standard approach in our master plan. I think that's really, at the end of the day, the biggest outcome is we were able to inform our intentions and aspirations for future development in our city's master plan. And our redevelopment partner has embraced that. They are very much able to see the value of that for many reasons. And I think that was really in part because we laid such a strong foundation, not just from a vision standpoint, but also to justify that through allowing this stormwater management system to meet these multiple objectives and to provide these multiple benefits.
Great. Thank you, Wes. We'll continue with Doug. Now, Doug is coming again from the Mississippi Watershed Management Organization, so a slightly different situation, but very similar parallels, and I think in how you make decisions and how you consider all the options. So, Doug, can you give us some more detail on how MWMO would approach this from that perspective?
Yeah, and I would agree entirely with Wes. We do very similar process for very similar reasons, even though we're not the land use authority. We don't own land. Anything we do, we have to do cooperatively with partners. So it typically ends up being one of our member cities or a department of a member city or with the private developers. So in one case where we've done something like this at Towerside, which is just east of the Minneapolis campus here, we worked with 4 developers on about a 9-acre parcel to develop or to look at what's the difference if each of those folks does their stormwater individually, what would the cost of that be? Or what if we made a district system out of it? What would the cost of that be? Well, it turned out in this particular case, it would be more cost effective to just do the one district system than to ask them to do all that work individually on their own properties. And we were able to also then retain a significant amount of that rainwater to be reused and to create privately held public open space as part of that system. So again, trying to optimize as many different things that people are interested in an urban setting that you can. We're working on another much larger project that's a couple square miles up at, I call it 1NE, but it's to look at some flooding issues in the neighborhood and on a golf course and little capacity issues in pipes, and how do we look at that thing in its entirety and try to solve as much of that as we can at one time, working to meet our goals for water quality and quantity and habitat restoration with the cities and the parks needs for that same area. So we're still working on that one, and then we have one more coming up, which is Upper Harbor Terminal, which is again more like the Ford site, which is a 50-acre industrial site that's being proposed to be redone. And there we have the additional issues of trying to work, not issues, but the additional task of trying to figure out how do we really work in social equity, economic criteria into infrastructure provision, because the neighborhood is asking us, well, if you're going to build this stuff, what's in it for us? How does this help support the neighborhood's continuing growth and existence? We don't have the answer to that. We are interested in speaking with people about how we might look at something like that. But if you're looking at a triple bottom line where you're trying to address all those issues as you go through a design for infrastructure or the design for the development itself, a kind of mix of housing, entertainment, public open space, what do all those things look like? How do you do that in a way where at each of those decision junctions, you're actually looking at what's the impact across all that very broad economic, social, ethics, that entire suite of things that people are asking to look at. I think the biggest question we still have is what's the metric you use? I'm not particularly comfortable always going back to a metric of $1, but I don't know what you use in lieu of that. And so we've been trying to think about what's that going to look like for us. And we're just undertaking that right now, trying to figure out where that's going to go. And I don't have the answer to it. I think it'll be fun figuring it out, but you know, at this point, it's one of those, how do I want to put it? It's one of the things that as you're trying to change the paradigm of how people do business, you end up having just lots and lots of discussions where you look at something, you step back, you look at it again, you step back, until you can finally get to a point where people are comfortable with the risks they're going to need to take when they put this new paradigm in place to move a project forward, because you're doing something different. It's, I mean, even talking triple bottom line kind of things with people, it makes, and they're used to a much more linear process of, I'm a road guy, I do roads, or I'm a water guy and I do water. Don't make me think about that other stuff. I know how to do this, right? I'm comfortable with it, and now you're confusing me. And once you invite complexity into those conversations, you really invite a lot of discussions, you know, about a lot of things. And water crosses everything, right? Water crosses your decisions about, or ag, urban, you name it, there's a connection to how we manage and use water. So you fight over water all the time.
Thank you, Doug. And Brett, so you already mentioned Argenta Hills, but you also mentioned some other projects too that have a lot of similar parallels. So can you give us a little more detail of kind of how you tackled some of these challenges and made some of these decisions about what's best and selecting near optimal scenarios?
Sure. And I think piggybacking on Doug's last comment about, when I think of Inver Grove Heights and Argenta Hills and some of the work we've done there, and that's a zero discharge approach. It's happened to be a landlocked area. They had, when they came forward, they realized, you know, just going down a gray infrastructure path was going to be fairly expensive and really wasn't going to meet other goals like water quality, even though it could convey water. So it took a while to bring in a new paradigm, and it took, you know, back and forth and many, many years. I look back at it now, you can realize it just takes some time to get forward with this idea of trying something totally new. So we eventually did rewrite the ordinances for that whole 3,000 plus acre area. We looked at different manuals, different approaches, and eventually got people to the point where I think we were fortunate in that there was a large cost to try to go a conventional route. So we actually, in our case, we could show a cost savings by coming at it from a different point of view, but they had to be comfortable with trying a different paradigm and approaching it differently. So I guess in that case, the green infrastructure was, without that, we couldn't have developed this kind of zero discharge system. It just brought a new technology, a new performance level to the table that we wouldn't have otherwise had. So that became part and parcel of how we approached it. So it's been interesting. In the Argenta Hills first development, we were fortunate to be on the design team because they knew this was going to be fairly important, precedent-setting project in that area. And we used several techniques. And like I say, for someone that likes a challenge, it was a fun project to work on. You know, I think for some it's maybe frustrating because there are different tools in the toolbox, but we could actually adapt it to the site. And I think one of those interesting moments was after the project and kind of Main Street entry area of the large commercial area and the new road that was built was put online. The developer came out and said, you know, I've seen this planning come together, but I'm still kind of blown away by how much nicer the site looks. I think that's also, I mentioned that earlier, I think that sticks with people, these co-benefits. And at the time, I don't think we were calling it triple bottom line, but you know, this walkability, this, you know, better aesthetics, this better kind of wanting to interact with that landscape is something that I think broadly has appeal to policymakers and the general public. Whereas, you know, if you want to talk about X% reduction in phosphorus or TSS, you lose most people except the water geeks in the room. So, you know, I think making sure that is the one of the nice things that green infrastructure and LID brings to the table is you now start to build other community benefits, co-benefits that really do resonate a lot with people. And I think that starts to broaden the discussion. In the Inver Grove Heights example, I think another strength that made all the pieces click was it was very much a combined sitting down with the land use folks and the planners at the table, along with the engineers and the road designers and looking. And so actually part of that whole package of new ordinances included some novel things for the city at the time of having narrower roads than they were normally allowing. Having reduced parking and some creative shared parking scenarios that they didn't normally do. We reduced setbacks. We added some densification. We had some open space set aside and some densification, which raised some people. I mean, we're going to those planning commission meetings and people saying, well, that's not the way we build our houses out here. And it's like, yeah, this is a different development pattern, but it's part of a different way and a better way of doing things. So it was took some doing, but it was kind of neat. It's now been neat to see these projects come online and actually create some distinctive neighborhoods that I think people are very happy with, and they can tell that there's something a little different and a little nicer than what they've seen in kind of more generic sense. And that is a new development scenario. So like an Edmonton where it's redevelopment, then it's a little different dynamic there where you are trying to fit things into difficult spots. And, I think like Scott's talk, one thing we learned was definitely keep coming back to a small scale and see if these big picture ideas and your models really do kind of land, and kind of look at it at a detailed level to make sure that this actually is making sense what you're doing. So you don't come out with a number at the end and you realize, well, that wasn't really grounded in something you thought worked very well. But I think that was, again, I think what they get excited about are these co-benefits, this kind of placemaking, the streetscapes being more activated, businesses being happier that people want to be on those streets and want to walk down those areas. I do remember one of the stories that sticks in my mind is we did a little design charrette with some training with city staff, and we had a example we wanted them to look at was they had a little dead end that they thought could be vacated and was near a school site. And initially it was kind of like, well, we could do stormwater with this. We could just kind of dig a area out. We could make a pond, or maybe we could make just kind of a large square rain garden there. But as people sat down and thought about it, they're like, well, this is right on a walking path. This is kind of an important part that connects this area of town to this area of town. This could be more of a walkway. We could do something more like a plaza here. So when people want to come out, we can kind of make the rain gardens move and kind of interact with the site. And so it was kind of very gratifying to me to see people coming up with ideas that they were excited about, because they were showing how they're meeting the stormwater goals, plus they're adding all these other things to the site and creating extra benefits.
That's great. It's exciting for me to hear how we're taking challenges, right? These are challenging situations, whether it's large scale, small scale, infill redevelopment, and really making them opportunities, right? To make changes to how we do things. So what I'm going to do now is I'm now going to turn to the audience and invite your questions. You should have plenty of fodder. We're actually going to start with an online question, and then we'll go to our in-person.
So the online question was asking, Scott, at the beginning of your presentation, you mentioned that using this kind of approach, you might be able to scale up from, say, one development project to something the size of the city of Calgary. But now that we have a diversity of viewpoints here on the panel, I wanted to ask, how do you envision that kind of optimization process being applied to your, the city of Calgary, maybe the city of St. Paul? Like, how do you get together that kind of data that you would need to run something like that?
That's a good question, in that it is challenging. You do have to support that with infrastructure data. Oftentimes, we were talking about H&H modeling, for instance, that has to have the backbone behind that is collecting that information. Is the information accurate? Having, for instance, all those rim elevations to be able to look at some of those metrics for street flooding and property flooding is necessary. So, so it starts out with a robust GIS and asset management information is really what it requires. And that actually becomes very difficult. So I think it's a great question, especially when you start looking at our watershed districts, where we have multiple municipalities, multiple levels of dollars to be able to support that kind of infrastructure and data. And so it definitely becomes more challenging as you start scaling it up beyond municipalities. St. Paul, Wes, I'll let you address that, but what it takes to do it, for instance, at just even a large city like St. Paul, compared to some of the watershed districts, would be a very different and very different challenge to be able to just have the baseline data to be able to do that optimization. I think that the tools that we use, the different things that we're optimizing upon, that's much easier. It's coming up with that baseline data that's probably the biggest challenge in that scenario.
Yeah, and if I could jump in, I mean, one of the things that I find so interesting, one of my colleagues asked me years ago at the start of one of these exercises, they said, what's the standard cost of stormwater management? And I looked at them, I'm like, you're joking, right? And they were in our financial services office, and they said, no, what's the standard cost? And they thought there was just an answer that was going to come out. And what I take away from that, partly in answer to the modeling exercise, the optimization, I mean, there's a universe of ways you can manage stormwater. And I think really being clear on what are the low-hanging fruit in terms of the tools in the toolbox is key. So you can constrain your analysis to a reasonable suite of practices. But then also, you know, just realizing too that there's so much variability in how you can reflect the economics and how you do that. And I do think local costs are a really big part of the discussion. Certainly, I wouldn't say the standard cost of stormwater is what they pay on the East Coast, because that's totally a different market. But also at the same time, I would caution too that, you know, there is some benefit in just relativity. When you go through the optimization process and all that, I mean, don't get too hung up on the numbers, because really what you are trying to do is just compare alternatives, a baseline to these other practices. So you don't always have to find that right number. As long as you're consistent about the way you apply things, you can get a relative comparison, and sometimes that's really what you need.
Doug, would you like to add, please?
Sure. So in terms of the data collection part of it that I had mentioned earlier that we've been spending about the last 6 years, I know we're working with all of our cities. We have or will have shortly almost all of the watershed with the XP-SWMM model and so water quality attached to that. We're just finishing up a model or an inventory of our ecological services that we've done with the park board. So, I mean, just creating that information takes a long, long time. So now that we have it, the goal is to figure out how to use it most appropriately to help us identify where those projects can be done in the watershed to support the goals that we have for the water quality and quantity improvements and the habitat improvements over the next few years. For us, we can identify those areas where we think it would be best to do the project, but at the end of the day, we end up waiting for the partners who have a road or transportation project or a parks project or a large scale redevelopment for actually us to come in and do something. So we can do part of the assessment where we think we can identify what parts in the watershed do we want to focus our work on, but then the rest of it is really going out and finding the partners that are necessary to develop a project and implement something. And that's a part of this that I think when you're thinking of optimization, you can, for us, it's a multi-step process as we're trying to identify where we can do the most good in the watershed. But then once you're there, you have another optimization process that you use to say, what's that project ultimately look like? Because we honestly don't know, and we don't know what the cost is going to be, because you don't know what the your site conditions are, what your redevelopment components are that you're working with. Is it just a transportation? So we're just working in right-of-ways, or is it more broadly defined than that? So it's a good question, though. It takes a long time to develop the necessary information to do detailed optimization like Scott showed earlier.
Yeah, I think the project comes to my mind. I mentioned Edmonton. There was a good database of GIS information, so that was a big starting point. They did not have a citywide model, so we couldn't really use that tool. So I think you just have to be adaptable and kind of think about what your baseline information is, and there are different tools out there that can do it. We ended up developing one for that, but there are different ones I've seen out there that you can utilize. And I think for them, it was just first getting those basic questions down. Is, will LAD make an impact? How big of impact? Is that something that we want to chart forward for our community to do? So we're able to successfully answer yes to both of those and give them a ballpark of what that would be. And then we had done some optimization to say what types of EMPs we felt like could go in different areas. But I think in reality, at the end of the day, they needed those first questions answered. And then what we started to see is much more of a, as Doug alluded to, there was a road project or a redevelopment node that was happening that really became as much of a, even though I could say this is the top ranked project, those may be the ones that make more sense. They can be done more cost effectively. There's already some other energy there. There's other things happening in the community. So that's where you want to go, in which case you can pull out of your system and say, well, this was the preliminary look of what we thought the BMPs would be. I think as others have mentioned, the final one may look different than what that preliminary one was, but at least that gets you close. It gets you past those first questions of, yes, these have benefits, and then you can dive in at that site level and fine tune it. And it may change from what you had originally done, but at least you have set the framework up there and the basis there to start heading down that path. So when these opportunities do arise, a big road reconstruction or a park project or redevelopment, you can come in with some kind of educated understanding of the system, general hydrologic understanding of where water goes, and then go ahead and do that final layer of design at that point.
That's great. Thank you. Other questions from the audience here?
So I have two questions. The first is the basis of some of the social and environmental economics. I know we've been talking about that a lot. I'm wondering, first question, do you suggest using Envision, Scott, or what was the process there? And then I'm curious, I believe that that's what was used on the Ford site, if I'm not mistaken, but I'll let the others talk to that. My second question is penalties for flooding in your optimizer software. Was that an iterative approach on the numbers there, or did you have a numeric dollar amount to point to through some sort of documentation?
Yeah, so I'll start with the first one. Envision, we didn't actually apply Envision. We first started with a triple bottom line tool that the city had developed, and then added on to that. So there were values, for instance, that they had in this a triple bottom line tool that was developed by the city of Calgary, by staff there. We did an evaluation of those numbers and continued on with the ones that we were comfortable with, those values, and then brought in some other aspects to it. And so so it was, again, not starting from scratch, but it didn't necessarily use just Envision. Envision is often really focused on, for instance, type of materials and things like that as a part of their approach. And we weren't at that scale. We were at a much broader scale and trying to look at broader benefits and impacts at Renfrew, but really scaling up to a larger Calgary site. So Envision is typically something a bit smaller, but a bit more defined than that. As far as the penalties for flooding, it's a great question, and something I wish I would have pointed out or had time to point out when I was giving it. So the penalties that we used were actually based on real flooding events that had occurred within Calgary. And so we had insurance data to be able to use to be able to represent that. However, it was imperfect because, as you saw with the context of Renfrew, it was up on that escarpment, and so it was more of a localized flooding, and there they used processes such as trap loads and so forth as kind of a local way of managing some flooding. And so they actually used depressions in their system and used those ICDs as a way to kind of control it locally. The flooding numbers, so anyway, the flooding is going to be more, and it was over curb topping and so forth. So it's more of that localized flooding. The numbers we were using for this, and this was one thing that delayed the project for a little bit, is we were trying to get numbers from the University of Waterloo that was doing a study similar, at least from a flooding perspective, to provide numbers for that area, and we were going to translate them over to Alberta and to Calgary. The numbers that we did end up using were based on riverine flooding, which is a different type of flooding scenario and different type of dynamics that are occurring with that. So there we have, the river fills up, it goes over its banks and affects all of the properties, which is very different than a localized flooding. And so where that affects, and I'll go back to that original graphic where it showed, for instance, all the basement backups and things like that. And part of the point of showing that was that it wasn't necessarily localized to one small area. And riverine is going to be basically based on topography, based on, right along the adjacent properties that are near that river. And so it's sometimes not, you have to be careful with the type of data that you use and to be able to translate it there. And so that's why I'm caveating that the type of data that we used for that was flooding, but we made some adjustments to say, okay, we're not dealing with riverine flooding. We are dealing with more localized flooding that's not riverine flooding. And so that's going to happen in a different way and have different costs. And so we kind of cross that over with some other localized flooding where we did have an example to know what that adjustment might be from those insurance numbers from the riverine flooding. And so this is where you have to be careful with the kinds of numbers you use because it's not, you could come up with what's called flood numbers, but is that representative of your system? Now, if we're going up to all of Calgary, certainly flood numbers might make sense in a lot of locations, but when we were representing Renfrew in this, we were trying to be as accurate as we could with that. And so we didn't want to necessarily directly translate riverine flood numbers to more localized flood numbers.
Would other panelists like to comment or respond?
I'll just real briefly say, because you're asking about the forward site. So real briefly, we used proprietary software by a group. The software is called AutoCase, and it's a sustainable return on investment analysis with these environmental and social factors built into it. But we also did take an envision-based approach as well. So we had 2 lenses that we were looking at. And I'll leave it at that. If people want to go online, the report's available. It's about 3 years old now. It's on the Capital Region Watershed District website, capitalregion.org. And you can look at it there. I know we're getting close to the end of our time, so I leave more time for audience questions. And if people want to get into details, we can talk later.
Go ahead, please.
And for our upcoming project with Upper Harbor Terminal, we haven't decided the model yet. We just know that we're going to be looking at this and trying to figure out what's the best way to do it.
Yeah, I think one example comes to mind is using a local sustainability metrics that was developed at the city. And one of the questions I really liked that they asked in the rating system that we ended up incorporating in was, what type of community gathering space and how close is it in terms of housing incomes, and using that as sort of an opportunity to do some green infrastructure in a way that you're creating an actual asset for the community. So that was one example. I think it's kind of nice to use that local context as much as you can. And then, yeah, I'm familiar with AutoCase and have used that somewhat, and it has some good things and it has some limitations. So it kind of depends, I guess, on your situation.
Good. Other questions from the audience, please.
Question on the flooding up at Calgary there. It appeared that it was kind of an open site, and the question is if you were flooding over the curb, was there any real impact on the foundations or the flooding of the homes at all? Because, or otherwise, is it just a storage system until the whole system can drain itself out with controlled release?
Yeah, so so there were impacts, for instance, to the homes themselves. There isn't a huge topographic change, and so it wasn't very far. That's why we use, by the way, top of curb as that threshold where if we were getting above top of curb, there was definitely potential to go into houses and basements and so forth. So because it's kind of that plateau above the river, if you will. So there was the potential for riverine flooding. But the other aspect of this, I hit on it just a little bit, is that those V's in that earlier one where I was showing the progression of the different design storm events, and that it was actually escaping outside of the Renfrew neighborhood. And really the purpose of that is that once it's leaving, we have these escape routes that it's leaving, we don't have control over it. And so it's one of those where, is it still your problem? And we considered, yes, it is. And so that was one of the things we were trying to put as an objective, is we didn't want water escaping overland through these other routes that we had no control over. And so we were, well, it could potentially create an erosion problem. It certainly creates a downstream issue for someone. And we didn't want to just take a hands off and say, well, not our problem. We wanted to limit that. And that's why we set at that boundary condition that we wanted to minimize that and have that to 0, essentially.
Other audience questions? Randy, please.
Thanks, Andy. So we've been paying attention. You do H&H models, and they're based on design storms and precipitation frequencies. We've already seen big changes moving from TP40 to Atlas 14, climate change projections. We're in the realm of non-stationarity now. And the trends in, say, the upper Midwest is we expect to get more of our rain from intense storms. So the question essentially, when you're doing these forward-looking exercises, especially out as far as 2076, how do you factor changes to precipitation frequencies into all this?
We can start anywhere. We can start anywhere.
Do you have a suggestion for us, or? Yeah. No, we were actually talking about this a little bit earlier, and I don't have the answer to it. We're thinking maybe we have to look at probabilities of a high end and a low end, and kind of work it within a range and then talk about it in terms of probabilities, not certainties. And then again, you're going to have to decide when you're trying to optimize your system, what's the risk you're willing to take. That's what it's going to come down to. So, you know, I think you do have to, I do think we've already seen that the types of events that we get are having an impact, and our system already can't deal with some of those. So just trying to deal with the change in the last 10 years is difficult enough, kind of. But I do think from a long-term planning perspective, I would definitely, if you're looking out 25 or 50 years, I would tend to assume a more of a, be very conservative and assume that worst case scenario.
Yeah, I think it's almost it's a little scary. I think that people seem to be slow to, you know, sort of confront this, because I think it is this thing that's heading towards us. And I don't think we need to point fingers. I mean, a system was designed the way it was designed, and there's really no blame to be established. It's just that we're in a changing world. And so now we need to be able to figure out how to adapt or else. So, I mean, I think, you know, your connections with the cities, I think, you know, trying to get that out there, get speakers out there that, you know, say, you know, which future do you want to be prepared for, or do you want to kind of be caught unawares, I think, you know, is a choice that cities need to take. And I think they're kind of slow to take that up. I think Burnsville, a few communities have started to want to go there and know what those answers look like so they can be better prepared. But it seems a lot of cities just are sort of, we're worried what the answer is going to be, so we don't want to ask the question. And I'm not sure if that's the best place to be.
You know, if I could just say real briefly two things. Number one, I think we could talk a long time about precipitation data, downscale forecasts, that sort of thing. But I think in the end, one of the biggest tools that engineers have always used is freeboard, right? So we don't know, we have this inherent uncertainty, and it's being amplified now because we're recognizing that we know less and less, and it's changing faster and faster. But freeboard is a really big tool that needs to be, you know, looked at, and that margin of safety is a big component. But I also think too, it's how as excuse me, as communities or as agencies and engineers, you know, how we frame level of service is going to be more and more important, not only for the infrastructure and assets that we currently have, and the design criteria has changed. So that performance, that level of service is now radically different. It's kind of what Doug was saying, you know, what's the risk that we want to take, and how do we recognize that level of service for a new asset built today may realize a different level of service, a declined level of service in the future, whether it's for flood control or water quality or what have you.
Now, I'll add on to what Wes said. I think that's a great point with the level of service, and especially when we're talking retrofits, where it's difficult to, for instance, in a new development scenario, yes, you might be able to have control over what that might be. I think there are all kinds of tools out there. You know, again, coming from the technical geeky side of things, we can do some downscaling, we can do spatial and temporal downscaling. I'm not sure that those are more accurate than a statistical approach either. You know, I think the probabilities, as Doug was talking about, is a great way to frame that in the future. And I think, you know, considering, and Dr. Wadzik talked about this in her presentation where she talked about over design and how maybe that over design becomes our freeboard, as you were describing, Wes, where that now is our resiliency that's built into these systems. And I think that I'm actually proud as engineers that we think about it that way, and that we have been including that as much as we can. Now it's still a changing scenario, and a non-stationarity doesn't add to that because we can't always use the past to predict the future. So I think that we just continue with having these. We have to include those margins of safety, whether it's freeboard or other approaches like that, and it's going to have cost implications, and we need to be able to communicate that to those that are buying and these products, and the type of protection and the safety that we're bringing into these projects by including that and valuing that, you know, whether it's through a dollar value or some other way, you know, protection of property. I think that's the communication that we need to be, you know, going for in this, rather than just saying, yeah, we can predict exactly what it's going to be, and so we're going to design to that. We all know that that's not the case, and so I think it becomes more of a communication issue and a recognition of cost, that this might cost a little bit more to be able to be ready for 2076 or 2050 or 2020.
We'll take one more question from the audience, if we have any. Any from the online audience, please.
Saying that since infiltration tends to be a big part of stormwater management in certain areas, what kind of consideration is being given into that in the management, both looking at the potential benefits of recharging the aquifer, but also the potential consequences of introducing new contaminants?
Surface water, groundwater connections, right? Pros and cons.
Yeah, great. It's something definitely struggled with throughout my career, especially I think it's that kind of siloed effect of, you know, if you're a surface water manager, you kind of, your world stops at when you start talking about groundwater, and like groundwater management people, they're like, well, don't get any of that surface water into our nice clean groundwater. So I think I've always been intrigued by just bringing those folks together and understanding what's a safe, responsible way to do that. I mean, in some ways we like groundwater so much because it's gone through this great nature's filter. So I think that we should sort of walk away from or ignore this, you know, nature's filter of letting the water go down through all these soil profiles, I don't think is smart. But it is true that if you're in a hot spot, if you're around a gas station or someplace like that, then yeah, that may be a spot where you're not going to automatically do infiltration, or it's going to have some precautions that are put in place. So I think there's a balanced way to do it, finding the right geology, the right soils, and including that whole kind of thought process and how you infiltrate, but also not do it kind of blindly without thinking through the whole systems approach. So I think just better cross coordination between the different water sectors is something we can still improve on.
Other responses, please.
Yeah, I agree. I mean, I think what we look at there is we're as concerned about moving existing pollutants in soils as we are about introducing new. So a lot of the watershed, since it's a fully developed watershed and it's had multiple uses over the years, I can't think of a project we've done where we haven't had some sort of issue with the existing soils. There's usually something in there that we either have to remove, or we want to cap, or we want to make sure that we're not moving it. And it's not only on our project site, it's adjacency to our project site. So there are often times where we would like to do infiltration. We might have soils that would be good for infiltration on site, but immediately down gradient, we know we have a hot spot. So we don't do infiltration on site. We have to do something else. We have to do a reuse or some other option. So, we are very interested in this surface water, groundwater interconnection, and what's that mean for the kind of practices that we can use, again, in order to achieve our own goals for that surface water improvements that we're looking for. It's just in fully developed urban areas, it's a constant issue.
And I think that sometimes I've seen that assumption as I go up, travel in different areas, that they feel like LID or green infrastructure and infiltration are equatable. Those are one and the same. I think it's important that more people are realizing that if you don't have a good site suitable for infiltration, there are still other tools available. So I think that's why our reuse is really on the rise, because it doesn't really matter if you have contamination or something. You can store that water and use it for some other beneficial use. And really, infiltration is not really part of the equation. So just keeping in mind, there are other options besides infiltration out there.
And I would say that almost for any system where we're thinking about infiltrating, that we take a risk-based approach. And what is the risk of that, for instance, having a contamination, like Brett, you were mentioning hotspots and gas stations, things like that. So that's a place where you may not want to put an infiltrating system. And so use a risk-based approach of whether we truly do want to infiltrate, and then considering whether there are other tools, if you're not going to infiltrate, that might be appropriate for those locations. The other side of this, I think, that often gets overlooked is that I think that we are not always putting the value of clean water and connecting those. We assume that groundwater is clean, but it's not always clean. And if it is, then it's a precious resource. And I think a lot of times we're not putting the dollar value on that, the use of that clean water, like we are for other things. And because we know there's going to be treatment costs and things like that if it's not clean. And so maybe part of the risk-based approach is considering the potential for either existing or future pollutants. I know there are pollutants today that we're not even thinking about that will be our pollutants of tomorrow. And one of those emerging pollutants, for instance, is PFAS. And one that's similar to one that we've tackled in the past, like MTBE, which is very mobile. It does not degrade at all, and it actually has quite a high requirement for treatment. And so there's going to be those things that are coming out that we can't address even today that are going to be substantial. And so we have to be ready to pay for the value of what it costs to have clean water, or to recognize that we want to preserve that clean water, and so we don't want to necessarily infiltrate in certain areas.
I think that kind of parallels something that we were talking about earlier, that groundwater might seem free, right? Because it's there, and generally we assume it's clean. It's relatively inexpensive to treat because it's mostly clean, but maybe that's a poor assumption looking into the future. So with that, to kind of wrap up as a capstone, what I'd like to do just very briefly is I'd like each panelist to imagine, if you will, we're sitting down at the first launch planning meeting for a large project, and whether that's an infill redevelopment type project or a large scale, single, complete new canvas project. What would you recommend to us as the audience, who are your project team members, as both things we should try to do, opportunities we should take advantage of, and challenges that we need to be aware of going into this that we really need to just be prepared to tackle? So what would you give as our kind of words of advice?
I think the multidisciplinary team comes to mind a lot. I mean, those experiences of working with planners and road designers and all these folks, I think you're going to end up with both a much better solution coming out of this analysis, plus so many fewer barriers if you've included folks. And I think you keep casting that more broadly, economic development people at the table, equity kind of questions I think are coming up more and more. So I think having a broader net early on is going to pay dividends later. So I think getting those folks to the people at the table is very important. And I think doing that anytime you're trying to do this large scale planning, kind of scale it down to a small example and just play it out and see what actually you get as a result. I would keep doing that all along the process, and keep checking these kind of big picture, what seems to make sense in your head and at a big picture level actually plays out kind of like you hope it will at the smaller scale.
Great, thank you.
I would just say, and I think Scott's talk really reinforces this, but I would just say, be clear about the question you're trying to answer when you're going through this type of triple bottom line analysis, particularly as you really start opening up the number of variables that you're trying to evaluate and scenarios you're trying to assess. There's a lot of interdependencies between all of these elements, and the more you can just be real clear about what question you're trying to answer, I think it really will help make sure that you don't get pulled in too many different directions, and really give you an opportunity to use the tool in the best way possible.
Yeah, well, mostly ditto, but I would also say that, for us, I think we're at a point with this idea of bringing in all these different aspects rather than just looking at that, I'm going to design a stormwater system like we've done in the past, is to have an open mind about what you're willing to accept and work with from all the different disciplines, and figuring out a way that, because they all have goals for their part of the thing too, and you have your own goals, but be open about and willing to discuss and compromise and trade off and whatever you have to do in order to get to answering that question or goal that Wes just mentioned. To me, it's a very iterative process, and you have to be willing to go through numerous steps and be willing to make some decisions along each of those things and then re-optimize and move forward. It's a moving target in my view right now. So that keeping that open mind and willingness to try new things and think about new approaches is really a valuable attitude to have as you move forward in it.
Yeah, great answers from the panel, my colleagues up here. Those are all fantastic, and I'll just really hit on each of them. Defining your objectives and metrics is huge, and so the goals. You know, some that Brett had mentioned earlier were things like for some of those projects were walkability, appearance, activated streetscapes, which I hadn't heard of that one. I think that's a great one. You know, places where communities can gather. Those were some of the highlights. None of those were actually engineering problems. And so that gets back to what Brett said about having those multidisciplinary teams. I think at the same time, you need to have multi-representatives from your stakeholder groups. So that's, you know, different ages, ethnicities, et cetera, from the stakeholders that are providing input to you. Because those are some of those metrics that they have that Doug was just mentioning. Those are also going to feed into them. Now, are you going to be able to address all of them? No, as Wes just indicated, there's no way all of those can come into your tool if we're using a tool. But we need to be able to consider those things. And so, again, I agree that great responses, we have to be adaptable and flexible on those things. And that gets the last point that Doug made, and that's having adaptive management. So build systems that can have changes and aren't just, you know, make them so they can be changed easily and not necessarily be static where it's going to take a major overhaul just to change anything on those. And that's, I think, a real challenge. But if we go into them thinking that, hey, we can put more freeboard on them, or we can increase, you know, by including this area that might be more storage, provide more storage or something like that. That's the kind of approach that we need to think for and use for a lot of our solutions.
Great. Well, thank you. I will then conclude our panel. Please help me thank our panelists.